All right, folks, in today's video, we're going to be talking about exponential functions. Let's take a look. I've got two tables that I want us to take a look at. First off, I want us to notice that the difference to get from 7 to 10, we add 3. To get from 10 to 13, we add 3. To get from 13 to 16, we add 3. And this should look very familiar because this is a linear function. This is linear because we have a common rate of change. If you remember, ladies and gentlemen, m is the difference between y2 and y1. So to get 3, we took the difference, we took the difference between 7 and 3. I apologize. We took the difference between 10 and 7, and we got 3. So m is 3 over 1. Our rate of change is 3 over 1. And that gives us our common difference. Our common difference is the number that we add or subtract from our outputs in order to figure out what the change is. Now, if we want to take a look at this table, this looks a little bit different because here we have a difference of 2, but here between 4 and 8 we have a difference of 4. And between 8 and 16, we have a difference of 8. So there's not really anything that I can add or subtract. How do I go from 2 to 4, or 4 to 8, or 8 to 16? What am I doing with these numbers? That's right. What I'm doing is I'm actually multiplying by 2. I'm multiplying by 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. And if I wanted to look a little bit closer at these outputs, these output values, I could say 4 divided by 2 is 2, 8 divided by 4 is 2, and 16 divided by 8 is 2. So what I have here, this 2, is not what I add or subtract, it's what I multiply. And you remember when two numbers create a fraction, we call that a ratio. So what we have here is we have a common ratio. An exponential function has a common ratio, and the common ratio is b, the base, and it's the ratio between output y value of 2 divided by a y value of 1. So the difference between a linear function and an exponential function is that we're looking for a common ratio. What is the number that I multiply to go from that I multiply in order to get my change? I multiply by 2, multiply by 2, multiply by 2. And that gives me the common ratio. The equation for an exponential function looks like this. Our output, f of x, equals a times the base, which we just got done talking about, the common ratio, times x, our input. And if you notice, what makes this the exponential function is called an exponential function because our input, our independent variable, is an exponent. So here, ladies and gentlemen, just as a reiterate, this is called the base, or this is also called the common ratio. And it's the number that we multiply by in order to see our change in our function. Now the a, you'll be happy to know, is our friend, the y-intercept. So in this function happens to have a y-intercept of 2 and a multiplier, a base, a common ratio of 2. So I could write this as f of x equals 2 times 2 to the x power. Let me come down and let's talk about a slightly different way of looking at this. This is our 3-column process chart. So here we're going to put our output values, but first we need an equation. Let's choose the equation. Let's just use the equation f of x equals 1 times 2 to the x power. Now remember, I said that this was the y-intercept. Let's just see if this plays out. Let's use this equation and input our values here and see if this works. So 1 times 2 to the 0 power. You remember, ladies and gentlemen, our rules for exponents: anything to the 0 power is 1. So really this is 1 times 1, and lo and behold, 1. So our y-intercept really is 0, 1. Let's try this again. So now we're using an input value of 1. So 1 times 2 to the 1 power. 2 to the first power is 2. 2 times 1 is, so 1 times 2, that equals 2. And look, my multiplier is 2. I've just doubled my output. 1 times 2 to the second power. 2 to the second power is 4. Multiplied by 1, that equals 4. 2 times 2 is 4. I'm doubling my outputs. 1 times 2 to the third power. And remember, folks, remember PEMDAS. In PEMDAS, I always do my exponents first, and then I multiply. So I always need to do my exponent first before I multiply. So 2 to the third power is 2 times 2 is 4, times 2 is 8. 8 times 1 is 8, and I've just doubled again. So this is the way an exponential function works. You always simplify the exponent first, and then you multiply. So sometimes you'll see, just as an example, something that will look like this. We'll have 3 to the x power. And that's all it says. Well, you say to yourself, well, where's the a? What's happening here? 3, since it's being raised to a power, has to be the b. It has to be the multiplier. It has to be the common ratio. And what's implied here is that your y-intercept, is 1, because anything multiplied by 1 is simply going to be itself. So if you see something that doesn't have a second number, then you know that the y-intercept will be 1. Let's take a look at some of the problems that we'll be working on in today's class. Let me move the camera over so we can take a look at it like this. So in today's class, we're going to be looking at some tables first. And what you're going to have to do is you're going to have to figure out, is this table linear or is it exponential? And I've done this one for us because we can see that the change here is 0.5. We're adding 0.5 every time. You'll have to figure out the slope, which is what we've done. And you'll have to figure out the y-intercept, which is given to you in the table. And then you have to figure out the base. Well, this is a linear function, so it doesn't have one. So I put not applicable. You'll have to figure out the domain. And I wrote all real numbers. This R with 2 lines. That means all real numbers. That means from negative infinity to positive infinity. All real numbers. The range is also all real numbers. And lastly, I'm going to ask you to write the equation for whether or not it's a linear function. You need to know y equals mx plus b. Or for an exponential function, f of x equals a times b to the x power. Let's just look at another example. Let me move the paper. All right, so here we have something that looks a little bit different. You can see that this is not a constant. We're not adding or subtracting the same number. In fact, we're multiplying everything by 3. So that means it's exponential since we're multiplying. The slope is not applicable. This is not a linear function, so there's no slope. The y-intercept is 0, 2. 0, 2 crosses the y-axis. Then the base is 3 because that's the number that we're multiplying by. The domain is all real numbers. And we'll look at this in just a moment because what we're going to need to do is we're going to actually need to graph our exponent. So this is the y-intercept. This is the base. And in order to really understand the domain and range, let's graph this. So let me pull up my calculator. Let's go to y equals. Let's clear this out. 2 times 3 power up and x. And I'm going to go to graph. And if you take a look at this graph down here looks like it's right on the x-axis, but we're going to take a look at this in just a minute and we're going to see that it's not. And then once it gets right around the y-axis, it starts to increase very quickly right up off the screen. Let's take a look at the table for a moment because I want you to see what's going on here. See here at 0, that's our y-intercept. And here it starts to get really big. You can see it matches the table that's here on the paper. So you know this is going up. So this is the domain is continuing to increase and the range is continuing to increase. Let's take a look though on the opposite side where it looked like it was touching the x-axis. So the domain values are going to continue to decrease. They're going to keep going. And take a look what's happening to our output values. They're becoming decimals. They're becoming fractions. So they're becoming decimals. They're getting smaller. They're getting smaller. Remember scientific notation. What this means is that there are 4 decimal places. It's decimal, it's 4 zeros, and then a number. So this is a really small number. Now there's 7 zeros and 8 zeros and 9 zeros and 10 zeros. It's still, we haven't gotten to 0. It's just a really small number. An exponential function never, ever, ever reaches the number that it comes close to. So this looks like it's going to touch the x-axis, but it never does. It just gets really, really close. So what that means is that for our range, it gets really close to 0, but it never touches. So all of our y values are bigger than 0 and less than infinity. All of our y values are simply bigger than 0. Let's take a look at another set of problems that we're going to be working on in today's class as well. Very similar. Instead of looking at a table this time, we're going to be looking at this graph. And in this graph, I'm going to ask you to find the characteristics, such as the domain. Remember, it goes to infinity and it goes to infinity. So it's all real numbers. We're looking at the range. So this goes all the way up to infinity. It doesn't stop. But when we come down and we find the lower bound, we see that it comes really close, and it's going to come really close to 5, but it's never going to touch 5. Now it looks like it touches 5 on my paper because I can't produce ink small enough to create a line that's fine enough that looks like it's getting close but never touches. The intercept is 0, 6, because that's where my point is right here. The asymptote. Now this is a funny little word, but it has to do with the range. If you see the range value, so the asymptote value is 5, and the range has a lower boundary of 5. And what the asymptote is it's the line. It's actually a line. The asymptote is a horizontal line that represents the boundary of the function. What number does it come close to? What line does it come close to but never touch? The asymptote is the line that it comes closest to but never touches. So remember our horizontal line, horizontal, y equals. This comes really close to y equals 5 but never touches. Therefore, this is the asymptote. As x approaches positive infinity, so as x gets bigger, what does y do? Well, y goes really far up, so it goes to infinity. And as x approaches negative infinity, so as we go negative along the x-axis, y approaches, all the y values pretty much stop right around 5. So the y values approach 5, but never actually get there. And we're going to do several problems like this. And that's our work for today.